So when it comes to e to power minus x and ln and sine, some people don't like to do the differentiation. Okay, sometimes it's not that easy. For example, this one, he said, well, find a positive solution of 2 sine x equal x. That's the same thing. Here's two functions equal to each other. He wants you to find when this equal to this. You basically put them in one side and you say, well, then he wants me to solve x minus 2 sine x equal to 0. It's the same if it's 2 sine x minus x equal to 0 too, right? That one that will solve this one will solve this one. Same root. So anyway, here's f of x. X minus 2 sine x. What's f of prime of x? Well, differentiation of x is 1. Differentiation of sine x is cosine x. No, the 2 is just because of the 2. So it becomes 1 minus cosine x. And here is the formula. Xn plus 1 is xn minus, that's f of x, divided by the f prime of x. And it's that formula that he basically used to generate that table. Right? This is what he called basically, he even made it just 2 brackets. But anyway, or like just numerator and denominator. But basically the point is that you have x of n and you get xn plus 1 from this formula. And that xn plus 1 become your xn, you substitute again and you get xn plus 1. Until the number basically just converge to the how many digits he wants in the solution. Right? So I guess he wanted 5 digits, so he got his 5 digits. And so here's 5 digits, here's 6 digits, and so on. Question about Newton-Raphson? It just requires you to differentiate one function. And this is the f of x. We did this before. I'll let you see it. So now, what is the alternative if you don't want to differentiate? Because sometimes the equation is really long. It's not just, I don't know the differentiation of sine x. Sometimes you are solving a really huge nonlinear equation. So it's not convenient to do the differentiation. For example, in the last problem in the homework, that's the nonlinear equation. Look at this. You are solving it for f. F is the root or the x that we are trying to find. So you have 1 over the square root of f, and here you have minus 2 log, and then inside you have the square root of f. So yes, you can differentiate, but like. Yeah, well, that's just a number. That's just a function. But it's like this is actually the formula for the Moody chart. Those of you who had fluid already know that this is the formula to generate the Moody chart. So anyway, for those really long equation, you don't want to differentiate, So what's the alternative? The alternative is this method. It's called the second method. So rather than using the tangent, so if this thing is f of x, and you wanted to get the tangent so that you can actually come up with a better guess, rather than depending on the tangent, you would say, well, it's hard to get. I rather depend on the second of the function. So this actually requires you to have 2 initial guesses, not just 1. So you should have xn and xn plus 1. And you get f of xn and f of xn plus 1. And then those 2 points, if you geometrically, this is what's happening, okay? Mathematically, there's a formula that will just substitute n, but I don't want you to just substitute without understanding where did this come from, okay? I want you to really understand where this formula comes from. It doesn't make a difference when it comes to the solution, but it's really important for your education to understand where those formulas came from, because maybe later you come up with even better formula if you really understand where those formulas came from. Right? So he basically say, well, this function can be approximated as this second. Okay? That line is a good approximation of the function. And that make this point the root. So based on that geometry, you can get that root, basically from this formula. All right? It's as if he's using Newton-Raphson, but the slope of Newton-Raphson now is simply coming from this triangle. Okay, so it's xn minus x minus 1 over fxn minus fxn minus 1, right? Or it's actually the inverse of that. So where this leave us? This leave us with basically this formula. So rather than having Newton-Raphson with xn minus fxn over f prime, you will have xn minus fxn multiplied by this. Okay. So the method basically will require to have xn minus 1 xn fxn minus 1 fxn, and the new root would be basically xn minus f of xn multiplied by that formula over here. That formula, which is simply xn minus xn minus 1 over fxn over minus fxn minus 1. Right? So that what happened. See, you start with those two guys, and he approximate this function as basically that second, and that gave him xn plus 1. And so what do we have now? We have three things: two initial guess and the new guy. You get the new guy with xn, and you could question now me basically which is xn. You started with 2. Well, you designate basically this is x naught, this is x1. So the x1 that you had, you stuck with this guy. Let's keep going. Now this x1 work with x2, and you get x3. x3 will work with x2 to get x4. x4 will work with x3 to get x5. Alright? So what I'm saying is that the two initial guess, you call them x0 and x1. And the x1 is the next guy in turn to play with x2. So the blue line here was the initial trial, and that gave us this guy. And then now you have two value, fxn and fxn plus 1, and you would use them to get a better guess. Or basically you had f0 and f1, use that to get x2. And then you have f1 and f2, use this to get x3. Alright? So here is an example. If x equal x minus x minus 2 sine x. You want to solve this, and here is the initial guesses. X not equal 1, x1 equal 1.9. Those are the two initial guesses. And the formula is simply xn plus 1 is xn minus fxn, and then you have xn minus 1 divided by fxn minus fxn minus 1. Alright? So this formula basically what you plug in those two guys to come up with xn plus 1, and you just keep repeating. Piece of cake. So let's see what the homework problem is. So the homework problem is, well, here is a function e minus x minus 10x equals 0. Use the second method. So you don't have to differentiate 10x and e to minus x. You don't want to differentiate this. Here's just my f of x. Okay, well, what you need is you need x naught and x1. You need to initial guess to start this. Alright, so are those two initial guess are good or bad? We'll find out. Sometimes they are not good, sometimes you just have to try them. This is, by the way, the function itself that we are trying to solve. So the root is actually here. That Excel file is already in Desire to Learn. So the root is 0.5 something. It's here. So I already wrote the formula for you. Okay. Again, what's the formula? Simply xn minus fxn multiplied by xn minus xn minus 1 over fxn minus fxn minus 1. You don't have to memorize it. It's written for you in the book. The quiz will be next week, will be open textbook. You can just pull the formula. But again, it's simply approximating the slope of f prime from Newton-Raphson by that second. Okay? So here's the first iteration. How can I get the rest? Just drag this. Didn't converge. Actually, it did converge over here. It's just because the function was 0, he had hard time to continue. So here is the root, 0.531, 0.531391. Right? So it's really very comparable to Newton-Raphson, but with the convenience of not having to differentiate. The bad news is you have to supply two initial roots. And you may think, well, what's the big deal? 0 and 1. Here you go. Not always. You know, sometimes the initial guess is really hard, especially for a problem that you don't really know. Huh? Sometimes it's really hard to come up with two initial guess. Question about the second method? So the problem with those things in the exams, huh? This was actually, I think, was in the final last week. The problem is that the students are not used to type on the calculator that quickly. And so solving this problem by hand, which would be the case in the exam in the midterm, would require a lot of time, especially if you have never solved a problem like this ever before. And it's like you are opening the textbook and like, this is how you solve them. Okay, let's try. And you are trying. It takes forever. So my advice is that you have to practice a lot. Not just with the Excel file, but you have to practice by hand. So even if the homework is asking you to do it by Excel, because that's also important, the exam will actually ask you, and the quiz next week will ask you to do it by hand. Right? So you have to practice doing it by hand, okay? And it's not enough that you know the formula in page 75. That's not good enough. When you solve it by hand, you realize that there are things that's easier that will make you go faster. For example, you would say, I don't want to keep writing xn plus 1. I will just refer to the previous line, for example. Things along those lines that make you go faster. Right? Also, maybe you would learn in your calculator how to store the function, so that you don't have to type e to the power minus x minus 10x. You can just write the formula in the calculator, so that you basically just feed the xn to variable a and then just run, and he will give you the function. Right? So just practice, practice, and practice. Questions? Very good. So before we go to the next section, let's actually look at the last problem in the homework. So this, for people having fluid mechanics course, they understand why this formula is. This is actually just the energy equation between the top of the reservoir till the end of the pipe. There's a tank, water is sitting in this tank. Because of the head, water will go through the pipe, there's friction in the pipe, that kind of reduces the flow rate, right? But you can, even if without fluid mechanics course, you know that the higher the Z, the higher the flow rate, right? Well, here's the formula that basically tell you this. Here is the Z and here is the V. Right? So for different Z, you can get the V. Again, in fluid 1, you will learn where this equation came from. Alright, so what's the big deal? He would like us to calculate the flow rate if Z equal 90 feet. So for Z1 equal 90, calculate the flow rate. The flow rate is, what's the flow rate? He said in feet cube per second. How can I get the flow rate? V times the area, right? So basically he's asking you to calculate the V from this equation. That's easy, I can get the V out. Huh? It's not even nonlinear equation. I just get V squared out of this bracket and it will be Z. The problem is this F. The F, that's the friction in the pipe. The F is function of Reynolds number, which is function of V. So the F that you are trying to find its value so that you can calculate V, it's actually function of V. Alright? And on top of that, so that then this make this equation nonlinear. On top of that, it's not a simple function of V, because it's even implicit value. Even if you know V, F is also an implicit. It's part of an implicit formula. So it's nonlinear equation inside a nonlinear equation. Okay? So what does he want at the end of the day? Well, we want to solve those two nonlinear equations, right? So, to solve this, there is actually a MATLAB file uploaded to your Desire to Learn. That MATLAB file is already written, okay? And all you need is to run it. And he will actually calculate for you not just the V, he will calculate the flow rate as function of Z. He will run different Z and he will run he will give you the different flow rate. So you just have to find out for 90, I just want you to make sure that you run it. So you run it and you find out that at 90, what was the flow rate? You got it? So you just have to run the program, find out what is the Z, when Z was 90, what was the flow rate? And the second part, he said, which method did he use to solve the nonlinear Coulomb formula? This is the Coulomb equation. So you want to go inside the program, try to put your eye on the right place where he solves this formula, and then you look there and you figure out, is it fixed point iteration, or is it Newton-Raphson, or is it second method? How could you tell? Just look at the formula, find out if does he have just x equal f of x, g of x, or does he have, seem like he's dividing f by f prime, or okay. So this would require you to actually use MATLAB, right? So for those who never use MATLAB, it will be quite a shock, maybe. So, first of all, you will have to actually find MATLAB. So when you go to the seat lab, again, main hall to the left. Once you go there, open any one of those computers. You open them with your OK state account. You will find MATLAB sitting on this is a Mac, all right? But the other one is PC. So you basically find an icon for MATLAB like this. Once you launch this MATLAB thing, you will basically open the MATLAB file that I have on Desire to Learn. So that MATLAB file on Desire to Learn, there are actually two of them. One of them is Coulomb M. So all the MATLAB file will have an extension M at the end. And homework 3, problem 5, 3013M. So that's the main program. That basically he varied the Z. You can look at the Z. He's basically doing the Z from 10 feet all the way to 100 feet. So he will run the problem for different Z. Right? And when he's doing the iteration over the V, because again it's non-linear just for the V, every time he will have to get the F. Okay? And it's really a very good practice when you are writing program in general and MATLAB specifically, is that when you have another, you should have one main program and then everything else should be in functions. So you should always be able to call those functions. So I made a function that basically just for the Coulomb. That's the one. So the two of them need to be sitting in the place where you're going to run. So those two files you're going to download from Desire to Learn. Okay. I think what is still here. So when you go to homework, you will see homework 3, the M file, help for homework 3 problem 5, and Coulomb. Those two guys, those two guys need to be sitting on the root or the folder where you basically are gonna work. And then using MATLAB, you basically tell him, well, file open, and then you open that main file. right? Again, what's the main file? It's this homework 3 problem 5, and within that program you will basically call coolproc. All right, now you look at this is the formula to write coolproc. See, the program is very small actually, right? It's not a big deal. You look here and you will tell me what is that. Is it Newton-Raphson? Is it second method? Is it just fixed iteration, right? And once you make up your mind what method it is, you just run. And so when he run, you will find basically he's plotting the Q as function of Z, he's plotting the, you don't care about those, and the friction factor. But basically you get the Q as function of Z, and you get the number, and he can even plot them for you on the screen as well, right? So I really would like you to have out of this homework, be able to download any MATLAB file someone give you, or you find it on the web, be able to run it, okay? And then the fact that you can open, you know, two different function, or a main program and function setting underneath it, so that you can look at where things are being done and how they are being done. Question about this? And you can see basically how things are done in MATLAB, and you will see that once you actually learn later on in computer method how to program, they are all the same, more or less, right? It just, you have to remember different syntax for different things, but a person who can write a program for C++ is the same person who can write for Fortran, is the same person who can write for MATLAB. What's nice about MATLAB is that there is also the graphic interface next to it. So unlike Fortran, when I was a student, you know, we used to write in Fortran, then we have to take it to TechPlot and then plot over there. Well, of course, if you have just one software for plotting, I mean, that software will be amazing, you know. So TechPlot can do things that MATLAB can never dream of doing graphically. But MATLAB is not just plotting tool, right? It's also the computational tool. So he kind of like hold the stick in the middle, you know. He do all the computation, he plot, and so basically it's really very convenient for a lot of simulation. And so a lot of professional engineers, they actually use MATLAB for their simulation. All right. So actually, anyway, so a lot of company actually use it, right? Question about this homework problem? You download the two files, you just run them, and you look at the coolproc function to see how it's being done, what methods are being used. All right, that moves us to the next section, the interpolation. This actually is very useful. It's even more useful than nonlinear equation. I don't remember how many times when I was a student that I used the interpolation in order to come up with a value during my solving problems for different applications. Right? So what's the interpolation? It's basically, you know, you have a table which you have values, and you would like to know what's the function in the middle between those values. Right? Just because the table is not basically fine enough, right? So he's basically saying that when you are doing it in the middle, it's called interpolation, but the same technique you can use it if you are outside. Say you have something like this, and you want to find the value outside the range that they did data. There is no guarantee it will really be correct, but you are basically hoping that the trend remain the same, and that's called extrapolation. So extrapolation when you are trying to go outside, interpolation when you are inside, between the data points. All right? So the Lagrangian interpolation is basically, here is the formula. And it may look a little bit confusing, but I'll show you an easier way to remember it. But anyway, you don't have a problem because, again, it's not really like you're trying to, it's not closed textbook, right? So the formula for the first order polynomial or linear Lagrangian interpolation is simply this. So you have 2 points, x0 and x1. You have two functions. You know the value there. It's f1 and f0. What do you want? You want to know at any x in between them, what is f. Right? So the black is the function. And you only know two values on this function. And you want it in the middle. What do? You are basically saying, I think this black function is the blue line. That's what you do in linear interpolation. In this drawing, it looks horrible, right? I mean, that function is not really that line. But if we do it only between, you know, between here and here, that's not a bad approximation. So what I'm trying to say is that if those two points are really close to each other, chances are that the function, the curve, doesn't have a chance to get away from the line, right? But if you wait long enough, you never really know what happened in the middle. Maybe things really go really weird in the middle. So the interpolation work really good as long as the function is almost linear. And that happens when they are really too close to each other. Alright? So this is simply just approximating the function as a line, okay? And so that's why this formula. So the function at x, what is it at x, which is actually this point? You are hoping it's this point, but you are getting this point. Okay, what is it? X minus x1 over x naught minus x1 multiplied by f naught. What's f naught? That's the value at x naught. Plus x minus x naught over x1 minus x naught multiplied by f1. Alright? Or simply, if you are doing it in y and x, you know the x's and you would like to get the y, that's how you write it. Okay? I have a better formula to remember. Okay, which this was the formula that I used when I was undergrad. They gave it to us like this, so it stuck in my head. So it's basically y minus y naught over y1 minus y naught equal x minus x naught over x1 minus x naught. That's the proof that it's exactly the same. It just, this is much easier to remember. Alright? It's doing the same thing. You have a table, you have two values. Mach number 0.5, Mach number 0.7. Here are the two functions. You would like to find what happens if it's in the middle. It's not 0.5, it's not 0.7, it's 0.6. What's the actual function? Use this formula. You know the x's and you're wondering what's the new y. Questions?
So you just solve for the variable that you
Right, you are solving for y. We'll see an example right now. So you actually, for example, like this. You have a table here. Here is x and y. So len 9 so the function is len basically. So when it's 9, when x was 9, the len was 2.197. When it's 9.5, it's 2.25. You're wondering what happened if it's 9.2. When x is 9.2, what is the y? What is len 9.2? Okay? So here is the formula. The y that you are trying to find, minus y naught over y1 minus y naught, is x minus x naught over x1 minus x naught. And here are the x's. Look at this. 9.2 minus 9 over 9.5 minus 9. Those are the x's that you want, that you know. And the y, you know y naught and y1. Those are the corresponding to x naught and x1. And you're just wondering what is the y corresponding to my x. When it's 9.2, what's my y? Is that clear? And just put the formula and get the y. So linear interpolation is very easy to remember, not accurate. Only accurate if it's not 9 and 9.5, but maybe 9 and 9.1, and you're wondering what is between 9.05? Like really everything is very close to each other. But when the range is big, the function could curve, and in linear interpolation is not a good idea. So what should we do? Not accurate? What should I do? Can you guess?
I think you calculated for natural log 9.2.
No, let's imagine, see, in this example, we actually know the function, right?
Yeah.
But sometimes the function, you don't know the function. It's just a table. Table of observation. Someone measured the temperature in the atmosphere. What's the function? There is no function. It's just at 50 kilometer, here is the temperature. At 60 kilometer, here is the temperature. At 70 kilometer. And you are trying to find what happened at 55 kilometer. What's the temperature there? What do you do? This is just this example written one more time nicely.
Log linear.
second order polynomial. So rather than first order, use second order polynomial. Rather than fitting a line in the function, you fit a second order approximation to it. That's pretty good because, you know, even if it curve on us, you know, with the second order polynomial, it's like you know those French curve that we had. It's like you basically you curve it and you fit it, right? The formula would require to make a second order. You need not 2 points. You need 3 points, of course. So here's the formula. You can see the formula actually. Ouch. The formula has actually 3 parts with 3 points. So you have to start with x naught, x1, x2. You need to have 3 points in the table. So again, that weather example, you know, not only you need to know 50 and 60, but you need to know also 40. So at 40 kilometer, what's the temperature? At 50 kilometer, what's the temperature? At 60 kilometer, what's the temperature? So then you can use those 3 guys in this formula to come up with the temperature at 55. Right? So here is again f naught, f1 and f2. Those are the actual value of the function at x naught, x1 and x2. And this those L naught and L1 and L2, those are basically those brackets. And you can see the trend. So if before with first order we only had x minus x1, but now we have x minus x1 and x minus x2 over x naught minus x1 and x naught minus x2. Alright? So not surprisingly, so here's an example to start with. Okay, and it's the same thing. So len 9.2, but using 3 values now. Okay, and so he's giving us, we need to give us a third initial value. So he gave len 11. Right? So you got the 9.5 and you got the 11 and you got the 9. So 9, 9.5 and 11, and he used all those 3 guys to come up with 9.2. Right? And so simply here are the 3 brackets that he multiplied by f naught, f1 and f2, and here's the formula, and he get a better approximation. And he's basically telling us, you know, with 3 lines, with 3 points, basically he can put a second order through the function. Right? So it's supposed to be better than first line, definitely. Right? Alright, so here's the formula for second order, and then you can imagine basically what happened. You can see the formula for higher and higher order later in the book. Alright? But I'm happy that you know the second order formula, because sometimes second order would be really needed. First order will not really give you a good solution. Alright? You have any question about this? So just again, here is the formula, simply this. As long as you know f naught, f1 and f2, and you get those 3 brackets that you multiply by f naught, f1 and f2, you will get the function at x, you get y at x that you want. Alright. Finally, the numerical integration. Alright, so there are 2 homework problems, and actually one homework problem in this. So this is the integration, right? And sometimes the integration is not that easy. It's much easier to differentiate than to integrate. Alright? So that's why numerical integration is really very good thing to learn. Alright? So geometrically speaking, the integration of f of x from a to b, this is f of x. Okay? I hope you can see from far away. Where am I? So geometrically speaking, if this is f of x, when you integrate f of x from a to b, it's basically you are trying to calculate the area under this curve from a to b. That's the secret. The integration is the area under the curve. So if it has to come up with the area, I can tell you, well, it's probably just the area of that rectangle. It's b minus a, that's the width, and the height is, I don't know, maybe I could just take the f of a. That's good. Or if you are not happy with f of a, maybe I could take the average of f of a plus f of b, right? That's the first and second method that we learned. It's called the rectangular rule, the trapezoidal rule. So in the rectangular rule, you basically look to this and you say, I see a rectangle. Forget about that small, and hopefully it's small, especially if A is very close to B. And if A is very far away from B, you basically tell yourself, well, let me do it into small parts. So rather than just one big rectangle, I will do it 100 times, 100 rectangle. So I will go A plus 0.001, A plus 0.002, A plus 0.004, and so on. And especially if the computer is doing it for you, it's not really a big deal. He can do it 1,000 times. And every time he's basically just doing that rectangle. Alright? So here is the first method. Simply just the b minus the a multiplied by f of a, the first function. Okay, and obviously that's the error that you are making. Alright? And the second method, that's the trapezoidal rule. You would say it's f, it's basically you're approximating the function no matter how does it look like to that rectangle, which is basically have the height of the average f of a plus f of b over 2. Alright? And so this is the rectangle, and when you do it so many times, tuck, 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 and the trapezoidal basically. Still, it's not good enough. So if you are modifying this, if you are inventing a new method, what would you do? I don't want to do it rectangle, I don't want to do it trapezoidal, I want to do it quadratic, right? Rather than approximating as a constant or approximating the function as a line, that's what you did here. You approximated the function as f, it doesn't change. You basically said, I think it will remain as f of a forever. That's a rectangular rule. And here you said, I think it's a line. The second or the third method or the third best is basically say, I think this is a curve. And for most function, especially if you don't go far away, they look like a curve. They look like a second order will fit on top of them. Or it's really a good approximation. Alright? So that's the Simpson rule. So let's first look at the rectangle. So again, the rectangle is simply, when you divide into so many times, it's h multiplied by the height of the first rectangle plus the height of the second rectangle plus the height all the way till the end. What is the height? That's the function at that point. Just substituting the function with this point, alright? And what's the h? That's the width of that rectangle. Okay? So if you're doing a to b, then the width is the whole thing. If you're doing it a to b but in 10 steps, divide that length b to minus a to 10 times. Alright? And the trapezoidal rule, because every time you are saying this plus this over 2, this plus this over 2, this plus this over 2, you'll find out at the end of the day, all the middle points get added twice, half from here and half from there. So it's as if you only have half the first one and half the last one, and everything in the middle just get 1, 1, 1, 1, 1, 1. Right? So when you do this by hand, basically you just get the initial value f of a, f of b, and f all the middle guys. You add all the middle guys, and then you add half the first one plus half the last one. And then you multiply the whole thing by h. Question? You have seen this before, right? High school? No? Not high school? Alright, so let's look at the Simpson rule first, and then we look at the example. So the Simpson rule is basically saying, well, let's fit a second order. Well, from the interpolation formula, that's the interpolation formula, right? This is the second order polynomial we have seen for interpolation. We are not going to use this formula. It gets much easier than this. But this is where this method is coming from. He's basically approximating the function as a second order polynomial. So what this will boil down to, it will simply boil down to this formula. So here is so again, to have a polynomial, second order polynomial, you need 3 points. Okay, so this cannot be done with only one interval, a to b. You have to do it in a plus b over 2, and then b. Right? That's the minimum. The minimum is 2 intervals next to each other. And you got f0, f1, and f2. f0 at a, f2 at b, and f1 in the middle. H is the distance of the interval. So obviously between a and b you have to have h and h. Does this make sense? Anyway, so what is the formula for the area under the second order polynomial, which is the approximation of the integration? H over 3, the first one, 4 of the middle plus the second or the last one. f0 plus 4f1 plus f over 2. Everything multiplied by h over 3. This will fit a second order under the curve. This will give you the area of a second order polynomial that meet your function at the beginning, the end, and the middle. And it's a good approximation. Especially, again, if you do it so many times, not just let's divide the whole thing into only 2 intervals. No, let's divide it into 80 intervals. Every 2 of them will basically be Simpson rule, Simpson rule, Simpson rule. Alright? So when you do this, when you divide so many times, you get 1, 4, 1, 1, 4, 1, 1, 4, 1. Every time it's the first one, 4 of the middle, last one. First one, 4 of the middle, last one. So when you add all those intervals together, what do you get? You will end up getting this. So this is the Simpson rule for so many functions or so many intervals. You still get h over 3. You get the last one and the first one and the last one, f0 and the last one. But then you get 4 of all the odd function. 4f1 plus f3 plus f5, and you get 2 of all the even one. So 2f2 plus f4 plus. Does this make sense? Alright, and so this would be the formula. So the computer program basically, or the algorithm for running something like this, is basically to have 3 boxes to collect those guys. A box where he collect the first and the last, a box where he collect all the odd one, and a box where he collect all the even one. Right? So the homework problem is this. He said do this integration using Simpson rule, and he wanted to do with 4 significant digits. Well, we are not iterating. Why we actually saying 4 significant digits? I think we just calculate the area, and whatever the number is, we just give it to him. No, there is a variable that you are iterating on. What is that variable? It's how many interval, right? So first of all, what's the function we are integrating? E to minus t squared multiplied by 2 to square root over square root of pi. That's the function. Alright? This is actually a very famous function. This is not just any number, any thing I'm throwing on you. This is actually called, can you guess? This is the error function. This is error functioning. This error function is this integration. It's called error function. It's so famous, it's so important. For example, in heat transfer, when basically if this is a hot egg, you know, that I cannot eat because it's so hot, and then I drop it in a cup of water, how cold it will get, the solution will have the error function. Right? So it shows up in so many applications. Alright? So they don't want to do this integration every time they solve a heat transfer problem or a wave equation or so they actually put this in table. There are tables for the error function. So for any x, so when the integration is from 0 to 1, that's the error function of 1. When the integration from 0 to 2, that's the error function of 2. So they have table for x and error function of x, or basically that integration. So we are doing it for x equal 1. So we are really integrating from 0 to 1, integrating this. Alright? So now from 0 to 1, how many interval? The minimum, of course, is 2 interval. 0 to 5, to 0.5 to 1. That's the minimum. Is that good enough? Will that give you the error function correct to 4 significant digits? So that's the point. You want to get the error function correct to 4 significant digits. How can I tell it's correct? You actually have table. Just search on the internet, Wikipedia, or look at the end of the book. We have in our book there is a table for the error function of x. So you can look for the error function of 1 and he will tell you it's point whatever. So I am helping you by giving you actually a MATLAB file that will do this for you. Right? So the MATLAB file, there's actually 2 files. One is called Simpson rule, okay, and the other, and that Simpson rule or Simpson basically .m, again you will run it using MATLAB. You will see that integration there. All you have to change is probably just the number of intervals and the limits. So maybe I missed rather than 0 to 1, I made it 0 to 2 or something for you, or maybe actually it's still 0 to 1. But you just have to make sure that the limits are correct. You are integrating from 0 to 1, and then there is a number of intervals. You play with it there. So you change the number of interval. You tell him do it for 100 interval, run. Do it for 50 interval, run. Do it for, right? And so every time he's doing that integration, he need to get f. He do it so many times. He have to get those f. So a good practice again is to take that f and put it in a function where he will ping the main program, the Simpson program will use. So that function is called my error function. It's called my error function. So in that my error function, it's basically what's there. It's this e to minus t squared. So you basically go there and you tell him t is 5. What is my e to minus t squared? You would say, well, that's so easy. Why don't you put it in the main program? Well, again, it's a good practice that you write the program so that he can use different functions. So that the Simpson program in this way, we can basically change my error function to project 2 and heat transfer function. It just integrate this one for us, right? And all you have to do is just add this function where it has this new big function. And the program, the Simpson program itself is running. Whatever function you throw in him, he will always call it, get its value, and you will see those 4 boxes where he basically collect all the odd numbers, and put them in, multiply them by 1, all the even ones, multiply them by 2, and the first and the last. Okay, I will finish the lecture by stressing it's very important to do those things by hand. Okay, do linear integration. There is a lot of example in our textbook, excellent example. There is also a lot of homework problem at the end of the chapter, and so you need to solve them by hand. You know, rectangular rule, trapezoidal rule, Simpson rule. Okay, because of the quiz, because of the exam, because of the midterm, they will all basically be on paper, not using computer program. Right? The computer program is just to make you appreciate, wow, this method is very useful. I can use it in my capstone, or I can use my heat transfer. But the hand calculation is very important for the quiz and the exam. We are done. Thank you so much.